In this video, I want to talk about the full picture of combining ideas of force length in muscle, force velocity, and activation to get a complete idea of how the muscle actually works to produce force. And there's two ways to think about it, and whichever one is going to make more sense to you is going to be dependent on whether you like to think about things visually, geometrically, or mathematically. So I'll start with the geometric interpretation because it kind of looks cool. Up here, we've got the force-length relationship that we just saw earlier. Notice here's the passive part of muscle, and here's the active part of muscle. And then over here we have the force-velocity curve, although the force-velocity curve, unfortunately, it's flipped around from the way that I drew it. So it draws lengthening going this way and shortening going this way. But either way, it doesn't matter. One way you can think about these as being is slices of a two-dimensional surface. And maybe I'll try and sketch this out over here with the other two curves in the picture so we can get an idea of what is going on. So we'll have to make a two-dimensional plot, we'll have to make a three-dimensional plot, which is going to be a little tricky. But let's put muscle force on the y-axis. Let's do muscle force on the y-axis, or z-axis, depending on whether you're an engineer or a scientist. And we'll plot going this way. Let's plot length, muscle fiber length. And then going off this way and this way, let's plot velocity. So velocity of 0 is going to be here. And then let's say going this way is concentric, so shortening. That means eccentric is going like this. And then we would have, on the length axis, we would have that optimal fiber length right about here, so 1.0 optimal. So, get to find out how good my three-dimensional sketching skills are. Let's put these curves in kind of like projected in 2 dimensions first. And what's the force velocity or the force length curve look like first? Well, it goes up like this, flattens off, and then goes down. And if we wanted to, we could actually include the active component as well. That's this part. Maybe we'll leave that off for the time being and then add it in later. Then, going this way, we'll want to add in the concentric, eccentric force velocity relationship. So, okay, that's going to start here because, of course, at 0 velocity, it's just the same thing as the muscle fiber. Force production, I should probably label my vertical axis here. Force. And now what's that going to look like? Well, in the concentric direction, that's going this way. So we're going to get like a drop off like this. And it's going to go down until whatever this Vmax is. Whatever muscle fiber shortening velocity that is. So you can start to see how this is going to form like a three-dimensional shape like this. And then it's going to go in the other direction. It's going to go up like that, right? It should be like that. So I'm going to try and extend this down and fully map out this three-dimensional shape. So if we took slices of it, we would see our old friend, the force length curve like this, and the force velocity curve like this. And this big kind of bump mound thing is what this figure is trying to get at. If we added back in the passive part, which is here on this chart, what would we get? We would get, I'll maybe try and do it in a slightly different color. Instead of force length going up and then down, we would get it going first in 2 dimensions. It would go up, down, and then back up once the passive component of muscle started working against us. So we would get up, down, and then up like that, which means that this whole side of the sheet would start curving up. So it would go up something like this. So if you're not impressed with my 3-dimensional drawing skills, I have a different way of thinking about it, and this is actually the way I prefer to think about it. I prefer to think about it from a mathematical relationship, and I'm not going to write out an explicit numerical curve here, but let's just suppose that the force length relationship, we can write it as the force is a function of the length of the muscle. And we can also write the force is a function of the velocity of the muscle. So perhaps you remember in math class, you might have f of x equals 2x squared, and you make some graph of that, and it's like this. I'm saying f of muscle length equals some equation that we don't care about that makes a graph that looks like this, like our force length relationship. And I'm saying that f of v is the force velocity relationship, which makes some graph that looks like this, our force velocity relationship. And who cares what the actual equations are? I'm just saying what you can do to find out what the muscle force is multiply these two together. So whatever the value of the force length curve is, multiplied by whatever the value of the force velocity curve is, and this is why this is so great, suppose we want to take muscle activation into account as well. When we were saying we can just scale them up or scale them down, that is easily incorporated here as well. We can say the muscle force equals whatever the muscle activation is, that's going to be between 0 and 1. Percentage of muscle activation, right? Multiplied by whatever the value of the force length is, multiplied by whatever the value of the force velocity curve is. So if I said maybe we can work through an exercise here. Let's say muscle activation is 50%. The muscle fiber length is 1.1% of, or 1.1 times the optimal fiber length. And the velocity is, I don't know, let's say 0.5, let's say 0.25 of the maximum shortening velocity. You could, if you had a chart with actual numbers on it, you could say, okay, well, what's the force length curve's value at 1.1? Go to the force length curve, figure out wherever, that's the force velocity curve. Figure out wherever 1.1 is, read off the number, write it down, pop that number in right here. Figure out what the force velocity curve is at 0.25 times Vmax. So that would be, if this is Vmax, 0.25 would be like here. Figure out whatever value of force production that is. These are all going to be fractions of maximum muscle force production. So you figure out whatever that is, and you write that in here. And then you multiply by 50%. So 0.5 times whatever that is, times whatever that is. I like thinking about it this way, but it certainly looks cool in textbooks when you draw it this way. And I don't know what you think about my artistic skills, but certainly this is one way of understanding the combination. But the takeaway of all this is that if you want to know the force production capabilities of a muscle that is both not at its optimal fiber length and moving at some velocity and activated at some non-100% fraction of its activation, you just multiply all three of those values together.